Now let's see the mathematical aspect of introducing a dielectric material in between two parallel plates. So let's consider a rectangular dielectric slab placed in a uniform electrical field E0. Due to this field, the dielectric material will become polarized. The positive charge of the dipole will align next to the capacitor plate with the negative charge and vice versa. So basically, here this end we have the negative charge next to the positive charge and positive layer next to the negative plates, right? Next, this polarization leads to two main effects. The internal effective field. So there will be an internal effective field. So basically, the negative and the positive as a whole, right? Ignoring the middle part. So because of the negative and positive, it looks like, again, this is all it looks like scenario. So electric field line will start from positive till negative. This is inside and this is induced, right? While the external, as in this one, that will continue to exist as well. Okay, so let's move on. Let me put it in the middle actually. Okay, this is not an exam oriented diagram. No, just go over there itself. It's for you guys to understand. What you have to draw in exam is the second one. Okay, so let me mention that off. This is for exam, not for exam, because you guys will waste time. Let's not have that. Okay, let's move on. Net field will be the result is the net result in a net reduction of, sorry, I'm not reading it right. This results in a net reduction of electrical field between the capacitor plates with which is given by E naught minus EP. EP represents your, yes, polarized or induced. Okay, so I have used EP, so let me use that. So basically, after writing all of that, you guys have to draw this diagram. So this is your initial electrical field. And it looks like as if there is an electrical field over here. But actual electrical field exists between this set of pairs. Okay, so that's important for us to understand. That will reflect in the formula. So basically, let me put it this way. This pair and this pair will have their own electric field, and that is nothing but your induced or polarized electrical field is what the math will tell. But here in diagram, we are showing, if not, something else altogether. So as a whole, what will happen because of this too? The net electrical field will be something like this. The difference between them will be your E net. Okay, we're trying to understand this. By how much will it reduce is what we are trying to understand. Okay, so let's recall everything till now. Charge produces field, experience force because of other charges, and that is nothing but your study of electrical field. Now, from the concept of field, we went on to energy, potential energy, and so on and so forth. And end of it, we came to a device which can store energy and release energy when needed. We're talking about electrical potential energy, right? Now, this material can have different shapes, sizes, so on and so forth. But we can make it better by introducing a material in between. And that material can be a metal dielectric material. Dielectric materials are ones, they are insulators, but they allow the electrical field to move from one end to another end. But they themselves will not allow the current to flow through. Right? Physically, if they are touching, the charges will not rush through this. If it was metallic, it will rush through. So it will be just a wire basically. Okay, does it make sense? So now when we expose this dielectric material, it will have its own electrical field inside. The net electrical field looks like this. Technically it's not so, but say it looks like that. So as a whole, the effect between the capacitors that there is a net reduction in electrical field. So the net field will be something like this. This was the original field without this is the original field without the dielectric. This without dielectric, no dielectric. This is the dielectric and the capacitor plates having their electrical interaction. But for convenience, we have drawn this. So this is because of the interaction between plates and dielectric surface. Again, not to be written in exam, just for your understanding. And so the net is what? Just a second, sorry. Made a sorry, yeah. The net field between the plates after dielectric is introduced. So that will be nothing but E naught minus E P. Agree? So let's substitute stuff. So we know that an electrical field is given by Q by epsilon naught A. This is for what? For parallel plate capacitor. Parallel plate capacitors. And so this is equal to Q by A is nothing but your charge density divided by epsilon. It can be epsilon m, epsilon naught, whatever. It depends on the medium. Right? So this will be your initial scenario. And EP will be, I'll call this as induced divided by epsilon naught. Okay guys, again here why are we using epsilon naught? I told you initially that it's the interaction between the plates and the dielectric surface, right? So it's not within the material, it's outside, but just for the sake of drawing we have drawn this, so don't get confused. It's epsilon naught. Agree? Now, and the net electric field will reduce by E net is equal to the original field by kappa or kappa, whatever. I think kappa, yeah. So this is read as kappa not k, but I prefer calling it as k. Kappa is too much. So let's call it as k. It's supposed to be kappa, by the way. So all in all, therefore, E naught by Ka, right, should be equal to sigma by epsilon naught minus sigma induced by epsilon naught. We are trying to figure out the induced density. Okay, guys. So let's get an expression for induced density. So on the LHS, we have K epsilon naught, and okay, we need to rearrange. So let's see how much charge is induced. That's one of the expression that we'll make use of. K epsilon naught. So this will be epsilon naught, all of that will get cancelled. This is 1 minus 1 by k, so k minus 1 by k. Okay guys, so that would be your expression. So what is that we are looking at? This bit will be the extra bit of charges that can accumulate on the plates without increase in potential difference between the plates. So we just are looking at a possibility, a scenario wherein we have this amount of extra bit of charges or energy can be accumulated. That's what we ended up with. Okay, guys, let me kind of make it. I think I spoke a bit vague. Yeah, I didn't make it clear. See, when we have a capacitor and when we introduce a slab in between, what happens? The electrical field lines, instead of going from one end to another end, can end up with the dielectric. So it gives a lot more chance of things accumulating at this end. But how much more is what we are trying to figure out, and that's what we figured out as well. Okay, so how did we do that? Quite simple. We saw the initial electrical field setup, and then we are looking at induced fields, right? So if I have to complete the diagram, let's do this, right? The layer of charges. So this will be sigma, and this will be sigma. So we are looking at surface charge densities. And that would be induced. So by the way, this will be negative, this will be positive, and this will be negative, and this will be positive. Okay, I'm not going to write that, but yeah. Let me write over here. Okay. Negative, and that would be induced positive, right? It makes sense. So we are getting an expression with this, with this set of terminologies. So how did we do that? So we know that we can add and subtract vectors, and that's what we just did. So the net effect is that we have a reduction of the field by kappa, the dielectric constant that we know for a fact, and that expression we equated it to the other set of expression that we got from the diagram. And on substituting, we ended up with how much induced charge are we looking at. So that will contribute to the excess of charge, that will be the excess of charge that the plates can accommodate as of now. That is the extra bit of charges, right? And that's the expression we wanted, and we are looking at it mathematically. When we put numericals to it, we'll understand how many more and how it can influence and so on and so forth. Right, guys? Very simple concept, but yeah, there are a lot of things to remember in terms of numericals and formulas and all of that.